Welcome everybody to the Thursday Zag seminar. Today we have Swarnava Mukhopadhyay with us, and he will talk about Higgins connection for parabolic bundles. Swarnava, please go ahead.
Okay, yeah. So everybody can hear me, right?
Yes, I can hear you clearly.
Okay, good. Yeah. Okay, so I'm going to talk about Higgins connection for parabolic bundles. So yeah, so let me introduce the context of what things are, and then explain our main result, and then hopefully I will be able to give you some feel that why the
so now your sound is just sometimes a little bit I think glitching. Okay, like just getting lower voice.
So hopefully I will be able to give you some idea of what the main results are and what's the idea behind the proofs. Okay, yeah. So still you can hear me, right? Okay.
Yes, this is better now. Yes.
Okay, yeah. Maybe I just need to shout a little bit. Okay. So yeah. So what's the context today? So we have a family. So we have a family of say some projective varieties. So call this pi. Okay. So it's a family of projective smooth projective varieties, and suppose I have a line bundle on the top, and I consider the coherent shift. Okay, given by the push forward of this line bundle. So this is a coherent shift on S. Question is that the question that we would like to understand, or what people are interested in, is that when does or maybe not when does the bed, how can we do there exist a flat connection flat projective connection on push forward of it. So basically, what means that if you look at, if suppose or one can ask when this is a twisted D module. So is this twisted D module? Okay, so we will put so this is the context we'll be studying the question. So we will have some very specific L for us, very specific M, and very specific S, and we will see that the push forward of that of those things will be a vector bundle, and the vector bundle will carry a projective connection or a connection on the projective edge. Okay, so let me just go briefly through the notations. So I'll tell you what the role of aim is going to be. So what are the main players? So let me try to describe what aim is going to be. So what is M for us? This is the main result. So for now, so we'll start with a smooth projective curve. Okay, so you can either or you can think of it as a compact Riemann surface. So for the results, so we will mostly be working over characteristic 0, but some results are also true in positive characteristic. We will try to mention what are those. Okay, so we will have a compact Riemann surface or a smooth projective curve, and we will have some mark points on the smooth projective curve. We call it P1 up to Pn. So those will be distinct. Okay, and E will denote a vector bundle of rank R on C. Okay, so since in the title we have parabolic bundles, so that means we need some extra structures because we have chosen some extra mark points here. Okay, so what are those structures? So we need extra structures at the marked points. And what are those extra structures that I want is that, so first of all, so for every mark point P, I look at the fiber and I want a decreasing filtration or a flag on the fiber. Okay, so P is a point on the curve. So P is one of these P1 up to Pns. So P is one of these P1 up to Pns, and I look at the fiber of this flag. Okay, of the vector bundle E, and I want a filtration on the flag. Now I want a decreasing filtration. That means okay, and Kp is the length of the filtration. So Kp plus 1 is 0. Okay, so Kp is the length, and then I also look into integers Rj, whereas Rj is just the difference between the one flag plus the next with the next flag. So I'm assuming my steps are all strict. So these inclusions are all strict. So it's a strictly decreasing flag. Okay, so with this notation, I define these integers R P vector. So it just denotes the jumps in the filtration. So this is also called the flag type. So this records the jumps in the filtration. So this is what is called the quasi-parabolic data. So vector bundle along with some mark points and some flags or some filtrations on the fibers is called quasi-parabolic, and then it becomes parabolic if addition to those to those flags I choose some rational numbers which I am calling weight, and the rational numbers are all increasing and they lie between 0 and 1. Okay, and they're not 1. So this is important. Okay, so I'm going to denote. So this is what is. Let me call this the weight vector, and let me denote this by this. Okay, so in particular, so if there are no mark points in this set, if n is equal to 0, so then it's just the usual vector bundle. Okay, now so we have decorated this vector bundle with some new data. Okay, now what do we do with the new data? So if you're familiar with the theory in the modular vector bundles, one defines stability and semi-stability using degree, right? So what we want to do is that we want to have a decorated notion of degree, what is called the parabolic degree. So what is the parabolic degree? So see, I have this vector and I have the vector that records the flag type, right? So it's the usual degree. So as usual, you have the original degree of the bundle, okay, of the underlying bundle. So ignoring the parabolic structure, but somehow we need to also record what is happening in the parabolic structure. So what we do is that we just take the vector P I, and I take the dot product with the number. So think of these numbers as vectors and look at the dot product. So this is producing a rational number, and I just take the sum from I equal to 1 to n. Okay, so this is like let me call this. So this is what is called the parabolic degree. So parabolic degree. Okay. And as you can imagine, if I, as usual, so if n equal to 0, so this parent degree of E is equal to the usual degree. Okay, so then one can define the usual slope. Okay, so the parabolic slope is just the parabolic degree divided by the rank of the bundle. Okay, so that's the parabolic slope, and using the parabolic slope, one can define a stability condition or a semi-stability condition in the usual way, in the sense that if I have if E is a F is a subbundle of F, consider the induced filtration and induced filtration on F, and choose the weights coming from E. So for example, if I intersect if at a point P, if I intersect with F and two filtrations coincide, I just take the weight for the bigger one. Okay, so and then I can say that E with all the decorations. So let me call it alpha and P is parabolic semi-stable if for all F subbundles the slope, the parabolic slope of F is strictly less than the parabolic slope of E. Okay. Now it is stable if this inclusion is strict, if this equality is strict. So stable if inequality is strict. Okay. So now there is a theorem of Mehta and Seshadri in 1980s who proved the existence of a moduli space. So that moduli space will be denoted by m bar, and then with the weight vector alpha with the vector, and then at the point C and the curve C. So what Mehta and Seshadri did, so Mehta and Seshadri constructed a moduli space that parameterized the semi-stable parabolic bundles of a given parabolic type and degree. Okay, so there exists a moduli space, and again this should be considered as a generalization of the usual case of G bundles. Okay, like the well-known moduli space of usual G bundles, and one can so there is also exists generalizations of this moduli space of parabolic bundles in the for parabolic G bundles in the works of Bhosle and Ramanathan. So that's in 1989, and which was subsequently generalized and by Bhosle, Balaji, Bhosle and Ramanathan were the first ones who claimed the existence of the moduli space, but then Biswas, Balaji, and Nagraj were the ones that give a complete proof of the existence of the moduli space for parabolic G bundles for arbitrary semi-simple group G. Okay, so as I mentioned, so if you ignore all the parabolic data, you just basically get back your original moduli space of principal G bundles on a curve. Okay, and that's a very well studied space, and this should be thought of as the non-abelian generalization of the Jacobian of a curve, of the Picard group of a curve. Because see, if you think of the Picard, it's like C-star bundles, a moduli of C-star bundles on a curve, whereas G is like a non-abelian group. So that should be thought of a non-abelian generalization of the usual Picard group. Okay, so for today, the role of M in here is going to be played by the moduli space of parabolic bundles. So this is played by moduli of parabolic bundles. Okay. So now I need to tell you what this line bundle L is. Okay. So you can imagine what S is. S should be thought of as moduli of pointed curves. Okay, and pointed smooth curves. And now I need to tell you what this L is going to be. Okay, so in the moduli setup, there is always a natural line bundle, which is known as the determinant of homology line bundle. So let me explain the determinant of homology line bundle. Okay, so suppose okay, so let me So suppose I have a family of curves, and E is a coherent sheaf on X. So let me draw the picture. Okay, so I have M. So M here is some you can take like some smooth variety. This is for any variety, so not necessarily the moduli of parabolic bundle. Smooth variety. And on top of this, so this is a family of curves. So this is a family of smooth curves, flat family, smooth curves. And suppose I have a coherent sheaf. Okay, so call this map pi. Then I can just consider the higher direct image of this. So I can just consider R pi lower star of E. And here I can, instead of I can look into the K0 of, okay, so this is an object in the K0 in the K group of M, and then I can define the determinant to be the determinant of the individual pieces. So recall that that this is nothing but the product of the determinant of R I pi lower star of E and then to the power minus I. Okay, so tensor I. Sorry. To the power sine to the power I. Okay, so that's the determinant of homology. So let me explain this determinant of homology and what is this line bundle, because somehow this is the main line bundle that we have with us. So since the fiber is a curve, the object R, so R pi lower star of E is represented by a two-term complex. So let's say call it F0 over F1, and if I take so it's given by a map, and the determinant homology is given by the determinant of this particular map. So for example, what I want to say is that the cohomology groups are given by kernel and the co-kernel of this particular thing, and if I take a point T in M, then the fiber of this line bundle at a point T is basically, not basically, exactly the cohomology of this thing. Yeah. Okay, so this is a very concrete description, and this is a very concrete line bundle, and the theorem of so this is a so date is a line bundle, so it's so date is a line bundle on M, and what Reze and Narasimhan proved in 1989 was that this is the generator of this determinant bundle is the generator of the Picard group. So also these things are ample. So this date, okay, so that's a very famous theorem of Reze and Narasimhan, and then for arbitrary, again this is for non-parabolic moduli spaces, and in the for SLN, but then subsequently if you replace this group SLN by G, then it was generalized by Kumar and Narasimhan and Bovin, Laszlo, and Polting. Okay, so one can study. So question one can study is that if I take these determinant line bundles, so call this det and its powers. Okay, so question is that so these spaces are known as non-abelian theta functions. So why are they called? What does it do with theta functions? Because if G is C star, then you just get a Picard group, and you are getting some natural determinant sections of some line bundles on the Jacobian. So those are exactly the theta functions, and here we are doing it for the non-abelian case. So this should be thought of as non-abelian generalization of the theta functions. And one can ask that how does these spaces depend as we move C. Okay, so that means if you change C in a Versal family, how does this thing change? Okay, so this is a well-known question. This answer is saying that as you move your V, these spaces glue together to become a vector bundle on the modular space of curves, and and in particular, their dimensions are the same. Okay, so in particular, so there's a formula known as the Validity Formula, computes the dimension of these spaces. Okay. Now one can ask, why are these spaces locally free? So how do you identify one space to another, right? So that's where the story of the connection comes in. So there's a so that's what I'm going to explain next in the next few slides. But let me before that let me denote the. But this is not our L for today. So again, I would like you to remember the picture that we have M, we have S, and we have a line bundle. Okay, and then we want to study push forward of that line bundle. Okay, and the existence of that connection. Twisted D-module. Okay, so since so this is so if M is just the usual moduli space, this is the setup. But now I am in the parabolic moduli spaces, so I need to modify. So I need to tweak my L here. So I need to make sure that the L now depends upon the choice of waves. Okay, so what do I do? So well, I'm given some choice of waves, so I'm just going to write them as in the they're all rational numbers, so I can write them in this form so that they are co-prime, and then I'm going to define L to be the LCM of all these BJs. Okay, so where J varies between 1 to Kp and P is in the set P1 up to P. Okay, so this is what is known in the theory as level. Okay, and what I'm going to do is that I'm going to rewrite this in terms of MJP divided by L. So I'm just going to multiply by so that the common denominator is actually L. So here, these things are integers, and then the last one, so MKP of P is less than M minus 1, and then they're all strict because I've chosen them to be because the alphas are all strict, and then the last one is greater than equal to 0. So 1. So this is the setup. And then I have a family of parabolic bundles. So what is the family of parabolic bundles? That means that I have a vector bundle, but addition to the vector bundle. So let's say if C cross S, so if C is a curve and S is a string, okay, and then I have a vector bundle E on C cross S. And what is a parabolic structure? Parabolic structure just means that if I restrict to Pi comma S, I will have some filtration. Okay, so this Fi is a filtration of the filtration of E restricted to Pi cross S. So once I have a filtration, and then I have the choice of weights. The choice of weights is discrete. So if it's a continuous family, it will not change. Okay, so then what I do is that I take the usual determinant bundle that I described in my previous page. Okay, and then for each jump and each point, I'm going to take the corresponding graded piece. So that's the graded piece in the thing is a vector bundle, so I can take the determinant and then I modify it by this particular weight that is coming from here, and then I take the tensor product over all j from 1 to Kp and from all p in P1 up to P. Okay, so this is the determinant of homology. This is known to us as the parabolic determinant of homology. And this was first discovered, I think it was first discovered in a paper of Narasimhan and Ramadas in '93, and then around the same time it was also used in a paper of Biswas and Raghavendra, which they gave an alternative description of this parabolic bundles, which are very important for in this particular question, so which I will hopefully explain later on. And also, this was also around the same time, was also present in a paper of Pauli. And also, I recommend a paper of Sun, where he describes these things very explicitly. Okay, so this is my role of the L. Okay, so this L I have now defined. I have now defined M and now defined S. Okay, so now I can study the space H naught of M alpha r of C, and then the line bundle for L. Okay, and then I ask the question, the similar question. So, for example, is there a how does this space vary if I change my C and P? Okay, so how does this spaces change with C comma P varying, and so in particular, in particular, how does this, for example, one can ask what is the dimension? All these things depend upon C and so on. Okay, so as I will mention in a moment that all these answers are well known. So what that there is actually a dimension formula, but those uses some infinite dimensional techniques in infinite dimensional Lie algebras. But however, for arbitrary groups and arbitrary parabolic bundles, I think a purely algebraic geometry proof of the dimension formula is not known. Okay, so so today I will give you another proof or just a purely algebraic geometry proof of this fact that the spaces don't change as you move the curve. So that's our main theorem. So the theorem is saying that if you look at the coherent sheaf, so again, so pi is the relative parabolic moduli space. Is you can think of them as the moduli space of curve. If you want to think of them as MGN, that's fine. Okay, and then on top of this, you have a line bundle, the relative line bundle, call it MG alpha, and this is pi. Okay, so this is the setup, and what we prove is that the coherent sheaf, when you push it forward, it carries the natural structure of a twisted D module as CP varies. So in particular, what I want to say is that if I look at the projectivized vector space MC par C and par alpha, and for two different curves, M alpha par for C prime, C par alpha, they are identified by parallel transport along a path, joining CP and C prime. Okay, so actually our results hold not only for the G bundle case, but also in the arbitrary semi-simple group. Okay, so our proofs are completely in the realm of algebraic geometry, and so let me mention the context of what motivated our construction, and also take this opportunity to explain that why this connection is called the Hitchin connection. Okay, because Hitchin was the first one that constructed this connection in the geometric fashion without using infinite dimensional Lie theory in the case of non-parabolic bundles. Okay, so let me briefly explain the context of geometric quantization. So geometric quantization is the following. So suppose I give you, okay, so this is the geometric quantization in the sense of constant and so RU. Okay, So what does one do? So one starts with a symplectic manifold and omega and a line bundle on it, and with a Hermitian metric. And omega is the, you should think of this omega as the curvature of the line bundles. Omega is the curvature form. Okay, so one can look at the L2 completion of C infinity sections of L. So that's in Hilbert space, and the yoga of doing geometric quantization is saying the following. So since M is a symplectic manifold, if you look into the functions, that becomes a Poisson algebra by where the Poisson bracket is just given by the commutator of the Hamiltonian vector fields. So what the process of geometric quantization is saying that, okay, so I have Poisson brackets, and the Poisson brackets get replaced by commutators. So what I want to do is that for every function, I want to assign an operator, okay, and on the level of so call this map Q, okay. So one can think of this as follows. So if I have two functions and I look into the Poisson bracket, okay, and I look into the Poisson bracket, whereas on the other hand, I can look into their commutators, okay, the image of the commutators, and where I is some number and h is some very small constant, the Planck constant. Okay, so this is the process, and this is some of the commutativity constraint that I'm mentioning here. Okay, so now Costin and Sarir say that, okay, whatever data we have is not good enough. We need more data, and the more data is the almost complex structure on the manifold I. So I is an almost complex structure. And under this almost complex structure, L becomes a holomorphic line bundle, and HI is replaced by the holomorphic sections of the holomorphic line bundle Li. Okay, so this quantization is exactly the same process where you are assigning, building up some Hilbert space, starting with some data of these line bundles. Okay, so now a natural question from the viewpoint of quantization is that the Hilbert spaces that I construct, how do they depend upon the almost complex structure I chose? Okay, so this is so Hitchin studied this in a very familiar context. So Hitchin studied this in the case of moduli of bundles, or in particular you can think of this as the character variety also by the Seshadri-Narasimhan theorem. So one looks at, so C is a smooth curve. One looks at the fundamental group, and then looking into homomorphisms from the fundamental group of C to the maximal complex subgroup of K. And then I take the conjugacy classes of that. So that's the character variety. And on the character variety, this is exactly also same as the modular space of bundles, modular space of G bundles. And on the character variety, there's a line bundle, which is known as the determinant line bundle. So this can be constructed on this thing directly and using the Quillen metric and so on. But what turns out that M has a natural symplectic structure due to the work of Atiyah Bod Goldman Narasimhan symplectic form. So M is naturally symplectic. However, if I choose an now C comes with a C is like the C has a complex structure. Someone can ask how the spaces H naught of Mi with the line bundle change as we vary I from C. Okay, so C is a fixed. So think of C as a fixed topological curve, and I is an almost complex structure. You're moving the almost complex structure, so your spaces MIs will change, and you can ask how does this space change? This is exactly the same question that I pointed out below, that I pointed out above. Okay, so this is okay. So this question has been studied again, as I mentioned, from a different perspective. So M can be constructed via affine Lie algebras. Okay, so this was a starting point of a very beautiful work of Tsuchiya, Ueno, and Yamada. So so they can, so starting with some affine Lie algebras, okay, so and some weights of dominant integral weights of some affine Lie algebras, they assign some vector space which they call conformal blocks. Okay, so on curve with mark points. So these are called conformal blocks, and Tsuchiya Ueno Yamada using Virasoro operators constructed a projective connection on the coherent shift B lambda. Okay, so there's a projective connection which I'm going to call the Tui connection. Somehow this is like the Lie theoretic connection, only works with characteristic 0, whereas you have on the other hand a natural identification. So this identification, I should mention, this identification between non-abelian theta functions. So these are the non-abelian theta functions, and the connection between these conformal blocks was first proved by Kumar, Narasimhan, and Ramanathan around 1984. Around the same time, there were papers by Boville and Laszlo for G equal to SLN, Laszlo Sargar for the parabolic case, and Pauli for parabolic SLN case, and also by Faltings, who more or less gave a first proof of the Verlinde formula using this correspondence. Okay, so and finally, one can ask. So as I mentioned, so what Hitchin proved was that Hitchin constructed a connection that identifies these spaces. So maybe I mentioned here that Hitchin is constructed that projective connection in a connection on the bundle, the vector bundle with fibers. Okay, so now one can naturally ask whether so on the same vector bundle we have two projective connections. One is given by Laszlo's construct, one is given by the Tui connection, the Tsuchiya Ueno Yamada, and the other one is given by Hitchin's connection, which we generalize. And one can ask whether these two connections are the same. And Laszlo proved that in the non-parabolic case, the Tui connection and then the Hitchin's connection coincide. Okay, so the Higgins connection from the geometric setup was also constructed by other people. So let me mention some names. So it was also constructed by Faltings. Okay, it was also constructed by Ramadas, and also it appeared in a paper of Axelrod, Della Pietra, and Wheaton. Okay, so these are okay. So now there has been more recently. There has been more algebraic geometric proofs, I would say, by Ginsberg, Zivran, also by Sun and Tsai, who also proved that geometrically that this connection has log singularities as you vary your curve to a nodal curve, and also by recently by Bayer, Bolognese, Martins, and Pauli. So Bayer, Bolognese, Martins, and Pauli's approach is completely algebraic geometric, very similar to Ginsberg's approach, and the key fact that underlines all the papers of Ginsberg's, I would say, Sun Tsai, and also Bayer, Bolognese, Martins, and Pauli is a very important result of Bailinson and Schickman that connects the deformations of the bundles, okay, with the deformation with the determinant of homology. So hopefully I'll be able to explain some of this later on. Now in the parabolic cases, this result was unknown for arbitrary G and so on. So let me mention the results that were known. So assuming the canonical bundle of the modular space of parabolic bundles has a square root. Okay, so this may not be the case. For example, you can just take, for example, the fibers could be like P2, and then that doesn't have a square root. So assuming this, there's a outline of a construction of this connection in the parabolic case for G equal to SLN in a paper of Peter Scheinost and Schloten-Loher in 95, but for genus G greater than 2. and recently Anderson and Metabier, using metaplectic quantization, very differential geometric techniques, they have been able to prove this, remove this square root assumption and claim to prove the existence of this connection for G, again for arbitrary G greater than or equal to 2. Okay, so this was the history that was of the problem that was known. So we solve it for arbitrary genus. Okay, so in genus 0 you have to be careful because you have to allow some more mark points, and then but for arbitrary groups and so on. So the main difference between Anderson Beer is that and us that we just work in a completely algebraic geometric setup where there's in differential geometry. Okay, so again, so now let me explain how this connection is constructed or what one needs to do to construct. So again, coming back to my setup. So question, let me address this question. How do we construct? Yeah, if there are any questions, please feel free to ask. I can take some questions now if there are. Okay, so let me explain the construction of the Higgins connection, and see what do we need to do to construct such a connection. Okay, so again, recall that we had M and we had S and we had a line bundle L. Okay, and we wanted some connection on here. Okay, so now let me enhance this commutative diagram by the following. So suppose C to S is a family of curves. So is a family of smooth curves. You can take Versal family curves. And M is the relative moduli space, but okay, so relative moduli space and modular space, and then I'm just going to take the fiber product. So this thing is the deformation of the curve. This is the deformation of the bundles, and this is like the joint deformation. Okay, so X is okay, so let me recall some basic facts. Is that if I look into the tangent space of the moduli of G bundles, or like for SLN, if E is a smooth point, then the tangent spaces are just described by H1 of the endomorphism bundle, and similarly for the parabolic moduli space, there is a similar description where you have to replace the endomorphism bundles by parabolic endomorphisms. So parabolic endomorphisms are nothing but it's just the endomorphism that restricted to that one particular point preserves the flag. Okay, so how does Higgins construction starts? So what Higgins does is that he considers this natural cup product map. So this is the usual cup product of cohomology. So here is just the H1 of the curve with values in the tangent bundle. So that is computing the deformations. That's exactly the taking care of the deformations of this line, whereas this thing is just the cotangent space of the bundle of the modular space at point E. Okay, and then if I take the cup product, as you see, this TC and KC cancels, I'm just left with endomorphism, and then H0 and H1 here lands me up in H1. Okay, so observe that end 0k of Kc dual is naturally identified with H1 of N0. Okay, so if I move this quantity to the other side, I will get a map from H1 to Tc to H1 C and 0 this square. Okay, so in particular I will get a map from H1 T0 to the symmetric power of the tangent bundle. Okay, because this product is this product is symmetric. Okay, so if you are familiar with the theory of Higgs bundles, this is exactly the quadratic part. This is exactly star. So star is the quadratic part of the Hitchin map. Okay, so you can ask what is the obvious modification in the parabolic case. Well, in the parabolic case, the similar story exists. You can also take the quadratic part of the Hitchin map of the parabolic Hitchin map, and here you just have to replace it by the divisor. And then here you get so for the power sin square t. So this is the obvious modification, but there are some non-obvious modification that I want to explain. So now again, now to construct a connection, what do we need to do, right? So we want to construct a connection on pi lower star of L. So that means we need to know how the sec. So we need to know. So we need to know how the variety in the line bundle and a section deforms. Okay. So this was already studied by Welters, and what one does is that, so if you have the modulus, if you have the bundle, so then the deformation is studied by the Kodaira spacer map. Somehow it's controlled by the tangent bundle. Whereas if you look at the line bundle, so you can look at differential operators on the line bundle. So that's denoted by di. So this means it is looking into differential operators. So these are comment. So these are differential operators of order less than I. So order less than 2. So yeah, so this means that this is what is the order. This order is denoted by this. Now see, if you have a differential operator on the line bundle and I am given a section, I can evaluate at some point of some section, and then evaluate at some section. Okay, so now this is 0. So these individual terms forms a two-term complex. Okay, so I have a map of complexes. So let me denote these complexes by d less than equal to 1 of L, S, and d less than equal to 2 of LS, and then this maps to the usual symmetric square of the tangent. Okay, so this is the one-term complex, and this is the symbol map of differential operators. So now one can look at the corresponding. So the point is that the hypercohomology of this complex controls all these deformations. That's the fact that was known by Welters, and so one can consider the natural map from the boundary map, not the natural map, from here to the first hypercohomology of this complex L, and let's just analyze what kind of maps do we have. Okay, how many maps do we have? Okay, so let's set up. So here is the base. So we have M, which is the relative moduli space. S is like the moduli space of curves. C is the universal curve, and X is the fiber product, right? So S controls both the deformation theory of C and also the deformation theory along the moduli of bundles. Okay, So if I deform my curve, my moduli space will also get deformed. So I will get a map here. Okay. So this map I'm going to call kappa. Whereas on the other hand, from here I have already constructed a map which is known as the which I'm going to call it as the symbol. So rho sim, the symbol map. And from here there is the boundary map. Okay. And the boundary map, it's a hyperchromology, but it contains information about both di, the operator, and also the line, also evaluation by section, right? But I can ignore the evaluation part, so I will get a map out here, some forgetful map, and again since the Picard group is discrete, and then there is and M is a projective variety, so it turns out that there is no H1 of the structure sheet. So this is isomorphic also to this to the tangent bundle. Okay, so I have got two maps. So one from here to here, one connecting the H1 of the C to TC to H1 of M via the Kodaira-Spencer, whereas on the other hand I have another map coming all the way through like this. Okay, so what Hitchin showed was that this. So let me call this this combination. So let me call this this combination. So let me call this this orange map. So this thing. So let me call this mu LK. Okay. So this because this the target and the domain doesn't depend upon the line bundle, but these maps individually depend upon the line bundle. So that's why this notation is being used. Okay. So what Hitchin proved was the following: that he proved the following equations. So he proved that this map kappa and the map mu L composed with rho sim. Okay, so that means I have this black diagram and then the entire blue arrow. That means I'm going from here and I'm going from here to here to here to here. They are related by this simple formula. Okay, and this fact I've already used it. So these are the three facts that Hitchin proves in his paper, and also he shows that using Higgs bundles, he shows that the modular space of bundles have no global tangent vector fields. Okay, so if these conditions are satisfied, Hitchin proved that there exists a second order differential operator. So let me prove. So Hitchin's theorem. So if above is satisfied, we have second order projective, because everything is defined up to constant, projective differential operator. That defines projective differential operator with symbol symbol rho sim that defines projective connection. Okay, so these conditions were so that's why I'm going to call this the Hitchin equations, and also you can call it the Van Gieman and de Jong equation, because Van Gieman and de Jong studied this problem in the more general context. Also, there is the same question was also studied in Hitchin's paper, but from the symplectic geometric context of scalar and scalar polarization. But just from the purely algebraic geometric context, what one can ask is that so what I'm claiming is that this equation makes sense even in the more general context of the deformation theory of a family of varieties. You don't need this part. Okay, so what does this mean? So let me just briefly mention, since I don't have plenty of time. So rho sim, you can think of it as a map from the tangent bundle to this pi to the to the push forward of the symmetric square of the relative tangent bundle. Okay, and you can think of kappa again as a map from S to R1 pi lower star of the relative tangent. Okay, so this is the general setup. You don't need all this. So all you need is the existence of some line bundle on which you want to produce the connection. So this equation makes sense even in the general setup of things. Okay, so again, so we will apply this general setup, but we need to work a little bit more. So let me briefly explain how Hitchin proved this equation. Okay, so give an interpretation. So it turns out that this map mu L of k. So mu L of k is a map from it's a map from, as you see, it's a map from the symmetric square. So it's a map from the push forward of the symmetric square of the relative tangent bundle to R1 push forward of the tangent bundle of this. Okay. So one can ask, what is this map? Okay, so k is some integer. So there's a result of Bailinson and Sheckman. Also, I think another proof is given in Bayer, Bolognese, Martens, and Pauli, that this map is nothing but cup product by some particular class. Okay, so now what happens is that since Picard group of Mg of C is Z, this class and this class are multiples of each other. Okay, so this is a multiple of K. Okay. So this is not true in the parabolic setup, and this presents a problem. Okay, so in the parabolic setup, the Picard group is more than Z, and that presents a problem. So again, ultimately, one has to. So if this is the case, so then one has to just relate how the deformation theory of the moduli space is related to the deformation theory by cup product by this class of line bundles, and that exactly was proved by Bailinson and Sheckman, combined with the works of Eno, with Bloch, Eno, and also by Ginsberg. So what they do is that they consider this sequence. This is the RTR sequence of the universal bundle, and then they take the dual. So if I take the dual, I have the duality algebra, and then the dual sequence. Okay, and then I can take a push forward. Okay, so if I take the push forward with respect to pi, I get an RTR algebra, which is an extension of the tangent bundle by O. So since my curve is projective, this is just O. And what Bailinson and Sheckman proved was that Bailinson and Sheckman, combined with works of Bloch, Eno, Ginsberg, was proved that that this extension class, this extension, and that this extension is same as the extension, the RTR extension of the determinant of homology line bundle. So once this is done, so you get a clear path of how this equation is proved. Okay, so now what we don't have is that, so in the parabolic case, this equation, there are two bottlenecks. So one bottleneck is that this fact fails for parabolic. Okay, and it's not clear what controls the deformation theory. What is the parabolic analog of this? Okay, so these are the two things that we address. So let me since there is no time, so let me just briefly mention that one uses these results of what are called pi gamma bundles. So given a parabolic bundles, one can construct another curve that is called C star, and I can construct a bundle with a gamma action, where gamma is the Galois group, and this and so suppose that if pi is a fixed point, then this action of the group gives the automorphism of the fibers. So that determines a particular representation of the finite group. So that is what is called the local type. And it's a result of Seshadri and Biswas, and also by Balaji and Seshadri, that this is an equivalence in the sense that you can reconstruct moduli of parabolic bundles via this correspondence. Okay, so and then one can also rewrite the Biswas-Raghavan result I mentioned in the beginning of the talk. One can rewrite the determinant of homology in terms of the determinant of homology on the moduli space on the curve upstairs. Okay, so one realized that so using this correspondence, one can construct the Atiyah algebras, which we call the parabolic Atiyah algebras. They're roughly described here. Again, I don't have any time to go through the details, but this is the so the context is so the right thing to do for us was to go to the parabolic moduli space, then look at the corresponding gamma bundles. That means the bundles which are equivalent with respect to group action upstairs, and consider the Atiyah sequence there, and take invariant push forwards. Okay, now that takes care of one thing, and then so in this, using this, we can generalize the result of Balians and Sheckman, and also Bloch, and so on. Okay, so that's how we take care of one of the problems. The other problem is that the Picard group is not Z. So what do we do? Okay, so in general, so we get an equation which is of this form. Okay, so which is of this form. As you see, if I knew that the class of L and the class of the canonical are related to multiples of each other, I can just club them together and have one thing. But that's not possible since this is the Picard group is not Z. But whatever it turns out that this multiplication map by this class of the line bundle is invertible. So I can just rewrite this equation in terms of this. Okay, so then this comes back in the setup of my Hitchin, Van Giem, and De Jong equations, and I know that this satisfies the so this equation. That means that I can find a differential operator whose symbol is exactly this. So this is rewrite this as all this the Hitchin, Van Giem, and De Jong equation for parabolic case. And once this equation is satisfied, as I said, that if you have so these equations are for arbitrary deformations of projective varieties. One, as I said, that if I can satisfy something, then we can find a differential operator that symbol, whose symbol is the given symbol. So now we have a complete. Now this is how we solve. This is how we address the question of. This is how we construct the parabolic Hitchin connection. So a natural question to ask whether this connection is same as the connection that Tui or the Tsuchiya no Yamada constructs in the conformal field theory. But however, we don't have a complete answer to them. I mean, if it's, we hope that this will agree. I mean, yeah, it will be really interesting if it doesn't agree. Okay, so I think I will stop now and I will take questions.
Okay, thank you, Swarnava. Okay. If anybody has any question, please go ahead. Okay, if there are no questions, I'd like to thank the speaker again on behalf of everyone in the seminar. Okay, thank you. That's a nice talk. Let me turn off the recording.
Yeah, thanks, Prakash.
Yeah, no problem.